We live in an environment that generates a constant stream of information. From temperature logs and stock prices to the contents of magazine racks, we are surrounded by a massive volume of individual facts. Any collection of these raw observations, the numbers, measurements, or descriptions that convey info about a subject, is what we call data. Navya and Naresh are starting with a very specific question. They want to identify the single most popular sport in their classroom. To find it, they go from student to student, asking for their favorite game, and writing the answers down in a single continuous list. Navya ends up with a notebook page containing 50 different entries. Every piece of information she needs is on that paper, but she still cannot identify the most popular sport at a glance. This collection of facts is currently inaccessible. Without a method to sort and process these responses, the list remains a barrier rather than a source of information. Sorting is the most straightforward way to begin organizing raw data. To see how this works, we can look at a list of shoe sizes for a class of 30 students. Recorded at random, these sizes are difficult to compare, but by rearranging the entire group into an ascending numerical order, the dataset becomes structured. With the list organized this way, the patterns become visible. You can immediately identify the extremes at either end and the most common grouping in the center. You can further condense this into a frequency table. Instead of listing every individual size 5, you create a single category and tally the total number of times that specific size appears. Moving data into sorted lists or tables is the required first step to transforming random observations into a usable format. While tables are effective, they still require the reader to process individual digits. To make comparisons faster, we can translate those numbers into a pictograph. For example, we might want to compare the total number of tractors owned across 5 different villages. A pictograph uses icons for quantities. To make the graph accurate, define the key, establishing how many units each symbol represents. This key allows representing fractional values. If one icon represents 10 tractors, half an icon clearly communicates a count of 5. These graphs are effective because they allow an audience to compare large quantities through visual scale, rather than mental calculation. Pictographs have limitations in precision. To handle data with more exact requirements, we use a bar graph. This chart tracks insects found in a sample. It relies on a vertical axis with equal increments, providing a fixed scale. Because the scale is fixed, the physical length of each bar maps directly to a specific value on the axis, allowing precise reading. A bar graph combines the visual impact of an image with the mathematical accuracy of a standardized scale. Choosing how to build a graph is an intentional process, where the layout should match the nature of the data. Consider a dataset showing the heights of the tallest students in your class. A vertical bar graph is the most effective choice here. The bars grow upward from the base, which helps mimic the way we naturally perceive human height. However, if you are graphing the lengths of the world's longest rivers, their names are often very long. In this case, a horizontal layout is more efficient. It provides necessary space for text labels without forcing them to overlap or become unreadable. This brings us back to the survey Navya and Naresh conducted at the start. By organizing the 50 random responses into a frequency table and then a bar graph, they transform their list into a result that is immediately identifiable. This is the practical function of data handling. It takes a collection of disconnected facts, processes them through a logical system, and presents them in a format that can be used to make a final decision.